wave function. So if you think of every system as being as having wave functions, which they all do, even particles are actually waves acting particle-like, according to people like Professor Dr. Sean Carroll. Um, the nature of, or the semantical nature of what time is has baffled people for thousands of years, but we have a wonderful model that fits the universe and conforms to the universe very nicely. The nature of it itself is actually a very simple notion. There is technically only one wave function, which is the wave function of the universe, and we are all just sub-wave functions of that wave function.
So, Mr. Michael, before we go on, can you please introduce yourself?
Oh yeah, sorry. My name is Michael Barry, Michael W. Barry, or whatever. I was a co-author for the book Helical. Natural Philosophy is the title of the book. Helical is the author, which also happens to be the name of a company that I started.
So, natural philosophy, did you describe how time evolved in the book?
Yeah, we built a model of the universe, and this is before we were able to talk to, or before we were able to intersect with Professor Dr. Neil Turok's left-handed chiral version, previous Aeon version of our universe, and our version basically starts from a quantum foam, and from that foam, a perturbation happens. It's just standard chaos theory. A perturbation happens, which normally it doesn't. Normally, perturbations aren't that big, but that's because they cancel each other out. There's always something in there that's canceling something else out. So, and it's called decoherence. As far as wave functions are concerned, it's called decoherence. Um, when one wave decoheres with another wave, it makes the wave smaller rather than larger. Um, Go ahead.
So, how do atomic clocks measure time and why are they so accurate?
Well, right now, and that goes along with our definition, actually, is as movement of the wave function, because as far as I'm aware, is it cesium 133, or sometimes they have variations of different materials. But what they do basically is they as an example for cesium 133, they count, is it like 10 billion vibrations of a cesium 133 atom is equivalent to 1 second. What we would call a second, or how a second is measured, is basically the amount um, of the amount of the Earth that has gone around the sun. So if you want to call, or the amount of, better yet, actually, it'd be the amount of Earth that rotated. But like, but so if you want to take the Earth and you want to put it on a unit circle, and you want to spin it, right? You want to spin it around the unit circle, and as you're spinning it around the unit circle, um, 1 second is probably like, I don't know, a couple kilometers or something, whatever that. Anyways, the second it's a measure of angle, sort of. And so what you're doing is just like, in some fashion, you're the old now. Okay, so this actually goes to the previous notions of what time was. So time was originally this thing. If you go into different cultures, it's some cultures will say it's left to right. So some cultures will say it's right to left. Some cultures will say that it's a meandering sort of nondescript, uh, like flow, or whatever it is you want to call it. Um, but nonetheless, there used to be this notion, and nobody had a unified, or a cohesive, let's just say a coherent um, uh, notion of what time was. So they attributed it to like mythological stuff happening, or they attributed it to whatever happening, like um, uh, whatever. The moral of the story is that eventually we found rigor, and with rigor we were able to communicate with one another more effectively. And by communicating with one another more effectively, we may not be able to speak the same language in terms of all around the world, but we can all speak ones and zeros, which is binary, which is Google has translators and stuff that you can use, that you can like speak, and it will like speak back to you in a different language. So we may not all speak, but we can translate, and that's due to rigor. And so rigor is the method that allows us to like sort of communicate from one culture to another, et cetera, et cetera, et cetera. Then we have the Julian calendar shows up. So you have this like sort of random eclectic um, consortium of people who are um, um, uh, paying attention to the environment around them and noticing environmental cues and how to base certain things like when to plant seeds or when to harvest or any of these other things based on those environmental cues. And so the notion then shifted from these random notions of whatever that was to a more mathematical version, and that was thanks to Newton and all these other people who believed in a Newtonian time frame, which is a single frame that happens in the entire universe all simultaneously, which it kind of does and doesn't at the same time, and that's due to the relativistic nature of the perturbation of wave functions. But I'll get to that. So, anyways, then you have the Julian calendar, and then which was Rome and all that other stuff, and then they had a pretty substantive calendar. As a matter of fact, because it's February 29th, in honor of leap day, leap year, all these other things. The reason why February is shorter than the other months is actually because what the Romans used to do was they had an official person that would say, okay, we harvested last year, and if we are trying to line up what our harvest looks like to what our harvest looked like last year, we have to add 20 days to February. And they would just add 20 days to February. And however many days you needed, they would either take them away or add them from February. And that's why February doesn't have the 30 days or the 31s like the other months do. So anyways, this notion of time was always this very elusive, notion. Then it became rigorous. Once we developed rigor inter-societally, we're able to develop this notion of rigor. We were able to translate and communicate in a semantical way rather than a syntactical way. So semantics rather than syntax. And by being able to communicate that way, all of a sudden you have the flow of ideas. It's like the internet, like the introduction of the internet. All of a sudden you have a type 1 civilization technology where we're talking to people from around the world, and we're able to communicate and translate between different languages, and we're able to take an idea and develop it worldwide, as opposed to and test it worldwide, as opposed to before we were limited to whatever a person could carry on a horse. So the notion of time itself is a very I mean, if you consider that it's what's trying to be communicated in some fashion is on a biological level, it's how long your telomere length is, because as you age, your telomere lengths become shorter because the number of copies of things that happens in your cell. So you have this thing that copies it, telomere length shortened for a biological system. It's telomere length. For an atomic system, it's alpha decay or beta decay or gamma decay, where where the system will release so much, or it produces energy in such a way that there's like a random amount of energy that's like a remainder, and that remainder turns into an escaping proton or an escaping neutron or an escaping electron. Yeah, go.
Very well said, Mr. Michael. But what is the theory of relativity and how does it affect our understanding of time?
Very good question. According to our model and our definition, movement of the wave function, and this is really where our model really, really does its magic, and that is, if you were to make a matrix, and you were to put inside of that matrix the gravitational constant, the local gravitational constant, the local electromagnetic waves that are interfering or commuting with whatever the wave propagation is that you're, the relativistic single wave that you're singling out. So it's like, you know how a sine wave goes up and down? If you were to take just the top part of one of those bumps all the way across the sine wave, that would be a single frame. So if you want to think of that as like a single frame, a relativistic frame. So as you watch that wave function now, and now as it expands, it's going to expand in 3 dimensions, and that's what the fourth dimension more or less is, supposedly. If you listen to them, anyways, if you make a matrix, you do the gravitational constant, the local commuting force, or the local commuting forces, the elaborated tensors as a dummy index, and I'm trying to think what the other one is. I'll look for it and I'll get it to you because it's in my phone. But anyways, you take these 4 numbers and you put them together, and what you're ultimately doing is you're calculating the total number of contributing forces that are going to have the effect or affect on the propagating speed of that particular wave function. Now, most of what relativity says is that in a vacuum, now this is all conditional stuff. These are all conditional situations. They'll say speed of light in a vacuum, blah, 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 blah. But the thing they don't tell you is that when it goes through water, they tell you it if you ask, but the thing that's not communicated immediately is that when it passes through things like water, it slows down. The photons are actually slightly slower than 299, 792, 458 meters per second. So because the photon is bumping into other like hydrogen particles and oxygen particles. Actually, particles are really waves acting particle-like, but I won't go into that right now. Anyways, the moral of the story is, if our definition of time is the definition that you're using for a model, which is movement of the wave function or propagation of the wave function, then what you're doing is you're setting time as the operator that produces the fluctuation. Now, it's important to say that the reason where Emmy Noether and Ludwig Boltzmann, where they got it wrong, was with this thought experiment. If you were to take a perfectly uniform singularity, perfectly uniform, or that is to say, without any defect, the distribution of energy is absolutely symmetrical in every capacity, and you were to take that and expand it into a thermal bath that is the same thermal state, or a translatory thermal state, to the singularity. As it expands, you're going to have a wave function without change. So you're going to have a singularity that expands into that thermal bath, but you won't. I'll put it this way: there's next to nothing you can do as an observer, as a subsystem of that universe, that is going to be able to allow you to observe that particular gravitational wave, or whatever it is, whatever you want to call that wave. And what that tells us is that wave functions are possible without change, without this notion of the Boltzmann version of, or actually it's Emmy Noether's version of, without Emmy Noether's version of change. And uh, Emmy Noether came, she wrote her proof on conservation of energy, there's actually a great there's a great colloquium by Professor Dr. Nikama. I'll have to look up the rest of the information, but it was a great lecture on Emmy Noether. It was a great colloquium on Emmy Noether. He goes through the math, the calculus, anyways, the moral of the story is the place that she was fundamentally not fully correct was that change is not what defines time. Change is not what defines the system. It's not entropy. It's not configuration. It's not hidden information. It's not any of these other things. It's literally just the act of the wave function of the universe moving in a particular direction that's internally causing all of the wave functions to also internally move. That is what you would call time. And then with that definition, it all of a sudden it follows relativistic effects, because now you have the gravitational system that is slowing down the propagation of the light photon as it passes, or as it goes through. And here's a great way to be able to resolve the wave particle duality. If you think about an ocean, right? So if you're on the top of an ocean and you're in a boat, when water is in the ocean, it's acting like a quantum system. But when the boat hits the water and causes the water to spray in your face, it acts like a classical system. So if you think about like photons or whatever as being, they're all in the ocean, but when you're moving through the ocean, sometimes you'll deflect photons in different directions and stuff. And so as the waves in different directions and stuff. And so as a result of that, you have the waves that are acting particle-like, and that particle-like nature would be what we observe as droplets of water. You can quantize that by saying the smallest possible surface area for hydrogen and for two hydrogens and one oxygen. So the smallest possible surface area for two hydrogen and one oxygen is going to be your quantization of what a drop is. So now you have a drop, and then you can take that and you can put that into a system, and you can say, okay, here's the ocean, and here's how the ocean behaves. Does the ocean behave like waves, or does it behave like drops? Well, it depends on if you're on a boat or if you're on the surface, or if you're under the waves. It's probably not going to act as much like, you know what I'm saying. So anyways, so that's the best way we've been able to resolve the wave particle duality thing. But to get back to your question, the single frame, the single relativistic frame that's expanding outward, that is your experience or whatever, it's going to travel differently depending on the gravitational constant, like I said, the other things that it's bumping into, like I said, the tensors that you're considering, which is the dummy index, and you know what? Actually, I can. Oh, and the Hubble constant. That's the one I was missing. I always forget that one. The Hubble constant is the actual wave function of the universe expanding outwards. So you calculate the Hubble constant, then you calculate then you calculate the local gravitational constant, then the local commutation of all waves. So what are the other things it's bumping into? And then what are the tensors, which is a dummy index? And then you have 4 indexes. You can create a matrix. From a matrix, you can solve that matrix and come up with a helical, and that's actually where the name of the book, where the name of the company and all these other names come from. It's because we believe time is helical rather than circular or linear, because a helix is both circular and linear. It goes in a circle shape, but it goes along a spiral, which makes it a line. So it is able to the way that, or the best analogy I think that I've heard from it was Mark Twain, who said, "History doesn't repeat itself, but it sure does rhyme." You have time as movement of the wave function. It observes these relativistic effects, which is described based on the commutation and by the commutation of all of the sum of all or the commutation of all contributing forces that result in the propagation of that wave. And then you follow that single wave or that single photon as it propagates outwards and outwards and outwards and outwards and outwards until it hits the edge of the universe, basically, which it never happens because the universe is expanding faster than the speed of light.
Very well said, Mr. Barry. But before we go on, I'm inviting you to listen to my other podcast, Book 101 Review, with my fourth season, people, fourth season. And please do listen to my latest episode. I interview one of the best aphrodisiac author in in our time, no other than Miss Amy Riley. So please do listen. Book 101 review. Plus, my books are out, not only one, but 3 volumes, people. Book 101, Volume 1, highly recommended. Volume 2, suggestion. Volume 3 is selected, available on Amazon and leading online bookstores worldwide. So, Mr. Barry, can time be considered the fourth dimension and why?
So the issue with time being considered the fourth dimension is that the similar way that we use the elaborated tensors is they put time as the 0th dimension as a dummy index. So time being the convention that it is, if you look at the Einsteinian equation, which if I'm not mistaken is r mu nu minus 1/2 r g mu nu lambda or something to that effect equals mc squared or whatever, or that's the way that works out or whatever. Anyways, the moral of the story is though. Is that it's a dummy index. So the mu nu part of the r mu nu, g mu nu is supposed to be this really, really big index where it goes x, y, z, and then you put t on there, and then you have t, so you have x, y, z, you have t, it goes down this way, and then you have x, xt, yt, zt, y, x, y, z, and you just go through all the permutations. And all of the other, basically what you do is you cancel out all of the and this is the current notion of time. You cancel out all the ones that don't work, and then after you cancel out all the ones that don't work, you're left with these 4, which creates a matrix, and then that 4 is those 4 are the Schwarzschild or the Schwarzschild solution for Einstein's r mu nu minus 1/2 r g mu nu lambda. Anyways, so when they talk about it being the fourth dimension, it's cheating. And it's blatantly cheating because, number one, it's a dummy index. So they say time is the 0th dimension rather than the first dimension because, believe it or not, prior to our current Descartesian notion of multiple dimensions or whatever, the convention used to be that the first one so if you look at a quadratic, for example, the x square would be the x, the next coefficient would be the y, the next coefficient would be the z, and there was only 3 dimensions, and that was the Aristotelian universe. That was the Socratic Aristotelian universe and convention. That math was only done that there was only an x, y, z plane. And then after Descartes, more than our dimensions, 3 dimensions. And then that's where we got this convention where it was like, okay, well now we got to like move dimensions around and like all this other stuff. But as time as a dimension, like I said, is in the current convention is cheating in the way that it's a dummy index. And just like the elaborated tensors are, and I'll be fully honest about the fact that, or fully candid, better, I'll be fully candid about the fact that that it's a dummy index, that we're putting, if there were something else that were more appropriate that we could possibly think of, I would love for someone to be like, hey, we've got a better index for you than a dummy index. So if for anyone listening, if you could come up with a better index than the elaborated tensor thing, that would be, we'll just leave that out there. Someone could do a better definition, but a mathematical definition. But either way, uh, time as a dimension doesn't really make sense, and that's because when you have, okay, x y, so in the mathematical convention, I'm not being provocative here. This is something that physicists do, and that when you hold your fingers like this, you have the x direction, you have the y direction, you have the z direction, and what you're doing is you're looking at the 3 degrees of freedom right here. So you've got x, y, z. Okay, great. So you have your 3 degrees of freedom, and then time is supposed to be the movement of those 3 degrees of freedom. Which, if you ask me, the only thing you're doing is moving 3 degrees of freedom outwards in an outwards direction, and that's cheating. To call that a dimension, to call that a degree of freedom like x, y, or z, I think is cheating. In my humble opinion, is cheating. And so, if you make time as an operator, and you take that operator and you use that operator, and you think of it like an operator, and you think of it like something that is going to manifest or generate different entanglement structures, maybe would be one possible way of putting it. I haven't put too much thought into it, but that whole notion of like, of time being linear or even circular, is to us, we said, I believe it's both at the same time, and and when you look at a helix, that's what a helix is. It's both a circle and a line at the same time, and it's just like very similar to the way that the Earth goes around the sun goes around the Milky Way galaxy. The Milky Way galaxy is headed towards the Andromeda galaxy, so those two galaxies are headed we're headed towards each other, and as all of those things are happening, as the Earth is going around, it's actually going it's going in a helical shape. Because the circle with the sun in the middle that you traditionally see, is that maybe a Keplerian version of the planets, all that kind of stuff. That's actually only from one perspective. That's only if you're looking down on the solar system. But if you look at the solar system from this direction, from from the angle of the plane that's the Milky Way galaxy, as it spins around the Milky Way galaxy, it actually spins around like this, and the sun's in the middle, so the sun goes like this, and the Earth goes around like this. And so the interesting thing is you would think that this would be a circle. You would think that the Earth comes back to the same point it starts at. But because the sun is also moving around the galaxy, it's not returning to the same point that it was relativistically. Does that make sense?
Makes sense. Makes sense, Mr. Michael, and very well said. So, how does quantum mechanics challenge our classical understanding of time?
Oh, that's a really good question. As far as quantum mechanics is concerned, there's an issue what they call time parity. There's an issue that they call time parity, and that basically the problem right now with quantum mechanics is due to the Boltzmann definition of time. If you were to take a movie of a wave function and you were to play it forwards and you were to play it backwards, it would actually be different going backwards than forwards. So if the movie, so if you were to take a movie and you were to play it forwards, right, and you're watching it, you see somebody jump out of a exploding car. They jump out of the exploding car, and there's an explosion behind them. You would think that if you rewinded it, that the person would come from the car. But it's not a guarantee in quantum mechanics. The person could come from anywhere at that point. The explosion can happen, and when you take the film, when you take the movie and you put it in reverse, it's going backwards, or inverted. It's not going to be the same. It's not going to take the same path that it took, supposedly. And that depends, and whatever. So, anyways, the moral of the story is that on some level they said that unitarity and quantum mechanics violates what I said about the Newtonian frame of existence, a single frame of existence that happens all over the universe, which it does. Because if you think about it, there's one moment that you can freeze the whole universe. If you were to freeze the whole universe, all the wave functions in the universe were to stop perturbating, they would stop moving. There would be no operators. There'd be no entanglement structure. There'd be no exchange of virtual particles amongst any system. So the whole system is frozen. If you were to do that, and then you were to push play again, everything would advance at a different rate because of gravitational differences, because of energy differences, because of all these other things that are happening inside of that space. So our definition as as time is moving to the wave function as an operator actually resolves both Newtonian and Einsteinian time, the time frame, the reference frame, in that movement of the wave function would be movement of the wave function of the universe. We are all subwave functions of the universe. And so you can freeze the whole, so you can set a single state of existence. Like I said, you can freeze all of the virtual particles, so nothing is interacting. No entanglement is exchanging. All the virtual particles are frozen. Every system is frozen. All systems would be frozen. There would still be a state of existence. There would still be a Newtonian frame there. But as soon as you push play, the Einsteinian frame takes over because each sub wave function perturbates at a different rate, if you want to call it that, or whatever. It perturbates at a different. The virtual particles are exchanging at a different rate than would be in another section, because, so for example, if you're close to a black hole, obviously there's only one place that all of the light is going to eventually go to. And actually, the best way for us to be able to test whether or not our definition is the valid definition is actually close to a black hole. What we need to find is the place close, as medial to a black hole as possible, in which the wave functions which come off of the electron, let's just pick a fermion, just pick an electron or whatever, that the wave functions that come off the electron no longer are able to come off the electron because of the gravitational collapse, right? So as the electron is falling down the well towards the point of dense energy, the PODE, that's what Dr. Susskind calls it, as it falls down the well towards the PODE, the vibrations that come off of the electron will keep getting slower and slower until they freeze. As soon as you see them freeze, that's where the horizon where I'm trying to find. And then so there's going to be that horizon somewhere, whether it's inside the firewall or whether there isn't a firewall. There's going to be that place where the wave function breaks down. There's going to be that horizon, and on that horizon, and beyond that horizon, the wave functions will stop perturbating. But that doesn't mean are now, according to the current model, there's a place in a black hole where they say time becomes space and space becomes time. My conjecture is that's the border or the boundary of the singularity.
Interesting, yes, Mr. Michael. Interesting thought about the universe and time. So if we sum up, what the importance of time in our time in the solar system that not governs the universe.
Um, in for the ability to have any intentful effect on the system. So any discipline. In our book, we describe higher order intentful effect that comes from or that comes from a living system. We describe it as discipline, and um, uh, from that discipline, um, the only way for there to be um, entropic favorability, in the words of um, yeah, whatever. It was a professor doctor at NYU. Anyway, entropic favorability is where I found the word, or is the word that I found, and it was great. The notion of entropic favorability. So we'll go with that for right now, and we'll say that in order to generate entropic favorability for one's system, you have to generate discipline. So the intent has to be there for now. Electrons will exist as like proto intent or whatever, but we won't go there. The moral of the story: in order for anything to be coordinated, disciplined, or intentful in the universe, we have to have this notion of time, or simultaneity. Maybe would be a possible definition. Um, and so without that, there is more chaos, and with that discipline, there is less chaos. There's more entropic favorability, and with that entropic favorability comes quality of life, more complex systems, um, growth of economies, and like I said, quality of life is hugely important. That kind of thing. So literally everything in your system that keeps your whole system coordinated, your entanglement structure, that is your skin and your bones and all that other stuff, your entanglement structure, the thing that coordinates your entanglement structure together. Without this operator, the entire thing would fall apart. The entire notion of having any living system would fall apart. Yeah, it would be pretty catastrophic.
Very well said, Mr. Michael. So, can you please invite our listeners to support their book, Natural Philosophy?
Yeah, if anyone's interested, a lot of our definitions and more are in our book, Natural Philosophy. By Helical is the author. The It's 36 pages. It's a very short read. It's like $10, I think, on Amazon right now. Definitely worth at least picking up a copy and looking through. It's thought provoking, and it also explains what I hope will be the rest of existence for life.
Yes, people, let's support Mr. Michael Berry or the Helical itself, because if you support them, more natural philosophy to come.
Thank you.
Mr. Barry, thank you for your time.